In probability theory and statistics, the multivariate normal distribution or multivariate Gaussian distribution is a generalization of the one-dimensional normal distribution to higher dimensions. One possible definition is that a random vector is said to be k-variate normally distributed if every linear combination of its k components has a univariate normal distribution. However, its importance derives mainly from the multivariate central limit theorem. The multivariate normal distribution is often used to describe, at least approximately, any set of correlated real-valued random variables each of which clusters around a mean value. Notation and parameterization: the multivariate normal distribution of a k-dimensional random vector x equals x1, x2, xk can be written in the following notation. Or to make it explicitly known that x is k-dimensional. With k-dimensional mean vector and covariance matrix. Definition: a random vector x equals is said to have the multivariate normal distribution if it satisfies the following equivalent conditions. Every linear combination of its components y equals a1x1 plus a plus akxk is normally distributed. That is, for any constant vector a(k), the random variable y equals or squared x has a univariate normal distribution. There exists a random vector z, whose components are independent standard normal random variables, a k-vector I1/4, and a car, a matrix A, such that x equals Rs plus I1/4. Here A is the rank of the covariance matrix I pound equals R squared. Especially in the case of full rank, see the section below on geometric interpretation. There is a k-vector I1/4 and a symmetric, non-negative definite car, K matrix I pound, such that the characteristic function of x is. The covariance matrix is allowed to be singular. This case arises frequently in statistics. For example, in the distribution of the vector of residuals in the ordinary least squares regression. Note also that the xi are in general not independent. They can be seen as the result of applying the matrix A to a collection of independent Gaussian variables Z. Properties: density function. Non-degenerate case: the multivariate normal distribution is said to be non-degenerate when the symmetric covariance matrix is positive definite. In this case the distribution has density. Where is the determinant of? Note how the equation above reduces to that of the univariate normal distribution if as a matrix. Each isodensity locus the locus of points in k-dimensional space each of which gives the same particular value of the density as an ellipse or its higher dimensional generalization. Hence the multivariate normal is a special case of the elliptical distributions. The descriptive statistic in the non-degenerate multivariate normal distribution equation is known as the square of the Mahalanobis distance, which represents the distance of the test point from the mean. Note that in case, along with the distribution reduces to univariate normal distribution, the Mahalanobis distance reduces to the Euclidean distance. Bivariate case: in the two-dimensional non-singular case equals 2, the probability density function of a vector, xy, a squared is. Whereas the correlation between x and y and and. In this case. In the bivariate case, the first equivalent condition for multivariate normality can be made less restrictive. It is sufficient to verify that countably many distinct linear combinations of x and y are normal in order to conclude that the vector, xy, a squared is bivariate normal. The bivariate isodensity loci plotted in the x, y planar ellipses. As the correlation parameter I increases, these loci appear to be squeezed to the following linui. This is because the above expression, but without the rho being inside a signum function, is the best linear unbiased prediction of y given a value of x. Degenerate case: if the covariance matrix is not full rank, then the multivariate normal distribution is degenerate and does not have a density. More precisely, it does not have a density with respect to k-dimensional Lebesgue measure. Only random vectors whose distributions are absolutely continuous with respect to a measure are said to have densities. To talk about densities but avoid dealing with measure-theoretic complications, it can be simpler to restrict attention to a subset of the coordinates of such that the covariance matrix for this subset is positive definite. Then the other coordinates may be thought of as an affine function of the selected coordinates. To talk about densities meaningfully in the singular case, then, we must select a different base measure. Using the disintegration theorem, we can define a restriction of Lebesgue measure to the dimensional affine subspace of where the Gaussian distribution is supported, that is, with respect to this measure the distribution has density. Whereas the generalized inverse and det is the pseudo-determinant. Higher moments. The kth order moments of X are defined by where a 1 plus a 2 plus a plus Rn equals k. The central k-order central moments are given as follows: a, if k is odd, I1 quarter 1, a euro, n, x a I1 quarter equals 0. b, if k is even with k equals 2i, then where the sum is taken over all allocations of the set into I pairs. That is, if you have a kth central moment, you will be summing the products of I equals 3 covariances. This yields terms in the sum, each being the product of I covariances. For fourth-order moments there are 3 terms. For sixth-order moments there are 3 AA, A5 equals 15 terms, and for eighth-order moments there are 3 AA, A5 AA, A7 equals 105 terms. The covariances are then determined by replacing the terms of the list by the corresponding terms of the list consisting of A1 ones, then A2 twos, etc. To illustrate this, examine the following fourth-order central moment case. Where is the covariance of xi and xj? The idea with the above method is you first find the general case for a kth moment where you have k different x variables, and then you can simplify this accordingly. Say, you simply let xi equals xj and realize that equals I florin I2. Likelihood function: if the mean and variance matrix are unknown, a suitable log likelihood function for a single observation x would be where x is a vector of real numbers. The complex case, where z is a vector of complex numbers, would be that is with the conjugate transpose replacing the normal transpose. A similar notation is used for multiple linear regression. Entropy: the differential entropy of the multivariate normal distribution is where the bars denote the matrix determinant. Kullbacher-Euro-Leibler divergence: the Kullbacher-Euro-Leibler divergence from 2, for non-singular matrices I0 and I1 is where is the dimension of the vector space. The logarithm must be taken to base e since the two terms following the logarithm are themselves base e logarithms of expressions that are either factors of the density function or otherwise arise naturally. The equation therefore gives a result measured in nats. Dividing the entire expression above by log2 yields the divergence in bits. Cumulative distribution function: the notion of cumulative distribution function in dimension 1 can be extended in 2 ways to the multidimensional case. The first way is to define the cumulative distribution function as the probability that a sample falls inside the ellipsoid determined by its Mahalanobis distance from the Gaussian, a direct generalization of the standard deviation. In order to compute the values of this function, closed analytic formulae exist. Another way to extend the notion of cumulative distribution function is to define the cumulative distribution function f, xo, of a random vector x as the probability that all components of x are less than or equal to the corresponding values in the vector xo. Though there is no closed form for f, x, there are a number of algorithms that estimate it numerically. Prediction interval: the prediction interval for the multivariate normal distribution yields a region consisting of those vectors x satisfying. Here is a dimensional vector, is the known dimensional mean vector, is the known covariance matrix and is the quantile function for probability of the chi-squared distribution with degrees of freedom. When the expression defines the interior of an ellipse and the chi-squared distribution simplifies to an exponential distribution with mean equal to 2. Joint normality: normally distributed and independent. If x and y are normally distributed and independent, this implies they are jointly normally distributed, that is, the pair must have multivariate normal distribution. However, a pair of jointly normally distributed variables need not be independent. Two normally distributed random variables need not be jointly bivariate normal. The fact that two random variables x and y both have a normal distribution does not imply that the pair has a joint normal distribution. A simple example is one in which x has a normal distribution with expected value 0 and variance 1, and y equals ax if x AAC and y equals ax if x AAC, where k is 0. There are similar counterexamples for more than two random variables. In general, they sum to a mixture model. Correlations and independence. In general, random variables may be uncorrelated but highly dependent. But if a random vector has a multivariate normal distribution, then any two or more of its components that are uncorrelated are independent. This implies that any two or more of its components that are pairwise independent are independent. But it is not true that two random variables that are normally distributed and uncorrelated are independent. Two random variables that are normally distributed may fail to be jointly normally distributed, that is, the vector whose components they are may fail to have a multivariate normal distribution. In the preceding example, clearly x and y are not independent, yet choosing C to be 1.54 makes them uncorrelated. Conditional distributions. If I1/4 and I are partitioned as follows. Then, the distribution of x1 conditional on x2 equals A is multivariate normal n, I1/4, I where and covariance matrix. This matrix is the Schur complement of I22 and I. This means that to calculate the conditional covariance matrix, one inverts the overall covariance matrix, drops the rows and columns corresponding to the variables being conditioned upon, and then inverts back to get the conditional covariance matrix. Here is the generalized inverse of. Note that knowing that x2 equals alters the variance, though the new variance does not depend on the specific value of A. Perhaps more surprisingly, the mean is shifted by. Compare this with the situation of not knowing the value of A, in which case x1 would have distribution. An interesting fact derived in order to prove this result, is that the random vectors and are independent. The matrix I12 I22 a 1 is known as the matrix of regression coefficients. Bivariate case. In the bivariate case where x is partitioned into x1 and x2, the conditional distribution of x1 given x2 is. Where is the correlation coefficient between x1 and x2? Bivariate conditional expectation. In the general case, the conditional expectation of x1 given x2 is. Proof. The result is simply obtained taking the expectation of the conditional distribution above. In the standard normal case, the conditional expectation of x1 given x2 is. And the conditional expectation of x1 given that x2 is smaller bigger than z is a. Where the final ratio here is called the inverse Mills ratio. Proof. The last two results are obtained using the result, so theta and then using the properties of the expectation of a truncated normal distribution. Marginal distributions. To obtain the marginal distribution over a subset of multivariate normal random variables, one only needs to drop the irrelevant variables from the mean vector and the covariance matrix. The proof for this follows from the definitions of multivariate normal distributions and linear algebra. Example. Let x equals x1, x2, x3 be multivariate normal random variables with mean vector I1/4 equals I1/4 1, I1/4 2, I1/4 3, and covariance matrix I pound. Then the joint distribution of xi euro squared equals x1, x3 is multivariate normal with mean vector I1/4 a euro squared equals I1/4 1, I1/4 3, and covariance matrix. Affine transformation. If y equals c plus bx is an affine transformation of where c is a vector of constants and b is a constant matrix, then y has a multivariate normal distribution with expected values c plus b1/4 and variance b pound bt, that is. In particular, any subset of the xi has a marginal distribution that is also multivariate normal. To see this, consider the following example. to extract the subset T, use, which extracts the desired elements directly. Another corollary is that the distribution of Z equals BAX, where B is a constant vector of the same length as X and the dot indicates a vector product, is univariate Gaussian with. This result follows by using. Observe how the positive definiteness of I pound implies that the variance of the dot product must be positive. An affine transformation of X such as 2X is not the same as the sum of two independent realizations of X. Geometric interpretation. The equidensity contours of a non-singular multivariate normal distribution are ellipsoids centered at the mean. Hence the multivariate normal distribution is an example of the class of elliptical distributions. The directions of the principal axes of the ellipsoids are given by the eigenvectors of the covariance matrix I pound. The squared relative lengths of the principal axes are given by the corresponding eigenvalues. If I pound equals Y out equals E12. T is any eigenvalue composition where the columns of U are unit eigenvectors and I is a diagonal matrix of the eigenvalues, then we have. Moreover, U can be chosen to be a rotation matrix, as inverting an axis does not have any effect on n, 0, I, but inverting a column changes the sign of U's determinant. The distribution n, I1/4, I pound is in effect n, 0, I, scaled by I1/2. Rotated by U and translated by I1/4. Conversely, any choice of I1/4, full-rank matrix U, and positive diagonal entries I yields a non-singular multivariate normal distribution. If any I is 0 and U is square, the resulting covariance matrix Y out is singular. Geometrically this means that every contour ellipsoid is infinitely thin and has zero volume in n-dimensional space, as at least one of the principal axes has length of 0. Estimation of parameters. The derivation of the maximum likelihood estimator of the covariance matrix of a multivariate normal distribution is perhaps surprisingly subtle and elegant. See estimation of covariance matrices. In short, the probability density function of a multivariate normal is, and the ML estimator of the covariance matrix from a sample of n observations is, which is simply the sample covariance matrix. This is a biased estimator whose expectation is. An unbiased sample covariance is. The Fisher information matrix for estimating the parameters of a multivariate normal distribution has a closed-form expression. This can be used, for example, to compute the Kramer copyright Ra bound for parameter estimation in this setting. See Fisher information for more details. Bayesian inference. In Bayesian statistics, the conjugate prior of the mean vector is another multivariate normal distribution, and the conjugate prior of the covariance matrix is an inverse Ashart distribution. Suppose then that n observations have been made, and that a conjugate prior has been assigned, where, and then, where. Multivariate normality tests. Multivariate normality tests check a given set of data for similarity to the multivariate normal distribution. The null hypothesis is that the data set is similar to the normal distribution, therefore a sufficiently small p-value indicates non-normal data. Multivariate normality tests include the Cox-Small test and Smith and James adaptation of the Friedmann-Frisky test. Mardia's test is based on multivariate extensions of skewness and kurtosis measures. For a sample x1, xn of k-dimensional vectors we compute. Under the null hypothesis of multivariate normality, the statistic A will have approximately a chi-squared distribution with 1/6 ak, k plus 1, k plus 2, degrees of freedom, and B will be approximately standard normal n, 0, 1. Mardia's kurtosis statistic is skewed and converges very slowly to the limiting normal distribution. For medium-sized samples, the parameters of the asymptotic distribution of the kurtosis statistic are modified. For small sample tests empirical critical values are used. Tables of critical values for both statistics are given by Rencher for k equals 2, 3, 4. Mardia's tests are affine invariant but not consistent. For example, the multivariate skewness test is not consistent against symmetric non-normal alternatives. The BHEP test computes the norm of the difference between the empirical characteristic function and the theoretical characteristic function of the normal distribution. Calculation of the norm is performed in the L2, I1/4 space of square integrable functions with respect to the Gaussian weighting function. The test statistic is. The limiting distribution of this test statistic is a weighted sum of chi-squared random variables. However, in practice it is more convenient to compute the sample quantiles using the Monte Carlo simulations. A detailed survey of these and other test procedures is available. Drawing values from the distribution, a widely used method for drawing a random vector x from the n-dimensional multivariate normal distribution with mean vector I1/4 and covariance matrix I pound works as follows. Find any real matrix A such that or AT equals I pound. When I pound is positive definite, the Kolsky decomposition is typically used, and the extended form of this decomposition can always be used in both cases as suitable matrix A is obtained. An alternative is to use the matrix A equals Y1/2 obtained from a spectral decomposition I pound equals Y out of I pound. The former approach is more computationally straightforward, but the matrices A change for different orderings of the elements of the random vector, while the latter approach gives matrices that are related by simple reorderings. In theory, both approaches give equally good ways of determining a suitable matrix A, but there are differences in computation time. Let Z equals T be a vector whose components are n-independent standard normal variates. Let X be I1/4 plus Rs. This is the desired distribution due to the affine transformation property. See also, chi distribution, the PDF of the 2 norm of a multivariate normally distributed vector. Complex normal distribution, for the generalization to complex-valued random variables. Multivariate stable distribution extension of the multivariate normal distribution, when the index is between 0 to 2. Mahalanobis distance, a sharp distribution, references. Literature.